Good morning. My name is Shui. Sorry I couldn't make to the conference personally. Hope this video can give you some idea about my PhD work. In my research, we proposed a application-aware network architecture and investigated how such networking architecture can improve modern applications performance. Me myself currently working at a big switch networks at Santa Clara, California. My PhD advisor, Professor Dipmati, is also in the audience today. In today's talk, I will discuss my research scope, the idea of AEN, and our motivations. I will also discuss two important applications in my research, Hadoop MapReduce and MPEG-reduced streaming. Our research idea is coming from the real-world application Hadoop MapReduce. We had some prior experience of using it to analyze campus NetFlow data, but soon we realized that our traditional data center network lacks the functionality to adjust applications traffic. We first investigated how MapReduce works and then summarized the performance limitation under traditional networking architecture. We then introduced our AEN concept, including the layer design, such as how we use SDN approach. We did a thorough testing. We then tried to generalize our method to any other applications. The basic Hadoop MapReduce workflow works like that. When clients submit jobs to the Hadoop cluster, the input data get replicated to different blocks. The mapper function starts before the reducer. Mappers and reducer belong to different hosts. When mapper finishes part, the results from the mapper get shuffled to the reducer. The shuffle data here we talk about matters a lot and has a great impact on the overall job running time. Our initial motivation is to reduce its running time from the networking perspective. The limitation coming from the Hadoop and the current IP network itself. Hadoop itself lacks a dynamic resource allocation. There's no mechanism to dynamically detect the suffer data. The traditional network itself, in general, lacks of a method to improve applications performance. And the underneath the best efforts resource allocation lacks a global view of real-time network traffic information, which leads to no dynamic traffic flow management. Our vision of AEN is to provide an intelligent network compared with the traditional one. It maintains current information about application that connects to it, and it can also automatically, dynamically, and continuously readjusting and optimizing application function based on the real-time network condition. And the ability to benefit from the application aware relies upon SDN at this point. SDN removes the control plane from the networking device and implements the functions in software, which enables dynamic control and gives the controller a comprehensive view of your network. Our AEN design took an SDN approach. There are two major components, physical switch white boxes and controller boxes. The switch box is nothing but a switch device, and using OpenFlow protocol communicated with SDN controller. It has no control plane. All the switching instructions come from the controller. The controller box is a physical control machine. We have designed into three layers. In the core layer, we implemented the basic networking function, such as LDP, ARP, ICMP, basically from layer 2 to layer 4. In the network control monitor layer, we took a REST API approach to proactively do network topology discovery, endpoint discovery, and shortest path calculation. And also we implement our traffic engineering to reroute traffic. In the application layer, we implement the Hadoop specific functions, such as SSH for node communication between Hadoop nodes, iPerf for background traffic injection, HDFS for Hadoop file system management, such as read and write, and also the MapReduce traffic shuffle control. There are many modules implemented in our design. Here are two examples to show how our AEN is flexible compared with the traditional network. The first one is ARP. ARP stands for Address Resolution Protocol. It is used by network endpoint to find the MAC address of another endpoint. It is a layer 2 protocol. In the traditional network, endpoint has no way to change the ARP behavior, and the biggest challenge of using ARP is to avoid flooding. There are many protocols out there to prevent ARP flooding package. Our solution is very simple, and there's no need of another protocols to prevent flooding. The logic here is to drop ARP flooding package whenever the switch saw the same flooding package from the same port for the second time. The major difference here between our approach and the traditional one is that we reduce the CPU cycle for dealing ARP flooding and improve networking efficiency. Another example here is our traffic engineering implementation regarding how to reroute Hadoop flow traffic based on the real-time network condition. Basically, what happened here is when the current Hadoop traffic flow path is congested with other background traffic, our SDN controller can detect in real time and readjust the flows. The new flow policy is synchronized with all the physical switches at the same time. In terms of the setup, we're using a real networking setup on Genie and a real Hadoop workload. We pick Highbench as our Hadoop benchmark workloads. Five Hadoop jobs were chosen based on our resources on Genie: sort, word count, scan, join, and PageRank. And in terms of the topology setup, we still using the classic 3-layer data center design. And all the Hadoop nodes are implemented in the leaf node. For the sake of comparison, we run our tests in both traditional networks as well as our AEN architecture, just wanted to build the benchmarks. Two results are showing here: the job runtime and the shuffle data. We found out that with the fixed hardware resources, the traffic of shuffling has a significant impact on job running time. By investigating the shuffle data pattern from the bottom figure, we found out that different Hadoop workloads have a different shuffle size. For example, PageRank has the most shuffle size, word count has the less shuffle size. So the problem of the Hadoop MapReduce job is that the pair of shuffle data between different nodes is highly unpredictable. It varies by a number of factors: replication factor, hardware resources, and etc. And it is impossible to know that how many pairs of traffic are coming from different pairs of nodes. So without those information, dynamic adjust traffic flows is very difficult. However, with our approach, the controller has a comprehensive view of the network traffic. It takes a snapshot of the overall network condition every couple of seconds. Here's one example to show how controller understands each pair of the Hadoop traffic. So for this particular job E3, we ordered the traffic pair by the size of the traffic size. We also know the timestamp of the traffic and where it's coming from. For this particular traffic, it has a 30 pair of traffic. Since the controller knows each pair of the traffic, we can now understand which link has the most traffic and if there's any bottleneck. The traffic rerouting logic will apply if any flow change needed. Here's an example to show how reroute happens in our topology. In this setup, path P1, P2, P3 on the left sides are chosen for running Hadoop jobs. Our controller also calculates multiple paths of shortest path for backups, such as P7, P4, P5, P6. When Hadoop traffic starts, we inject background traffic to path P2, P3. Here's the difference coming from between traditional network and our AEN approach. In the traditional network, Hadoop traffic will continue flows, as we already know that the jobs can run longer with the limited bandwidth resources. However, users don't know what happened in the neural network, so they just keep waiting and hope they can finish soon. But in our cases, on the right side, our controller can dynamically change the flow for you without your knowledge, and choose a different path. Here it will be P1, P7, P5, and P6. This figure shows the job completion reduction by using our AEN architecture. Based on the different job characters, we can reduce the running time by 20% to 300%. For example, the page rank right here on the right side, the shuffle phase has over 200% more data compared with the input size. But using our AEN architecture, we can reduce the running time by almost 300%. Here, we are trying to generalize our approach, and not just to running Hadoop applications. Since our design is layered, SDN-based approach, the core SDN controller layer can be easily ported to any other applications. The only thing we need to implement the application-specific and reuse our underlying modules, including the core SDN controller, network control, and the monitor layer. The next application we invested in our research is about MPEG-Dash video streaming. There are three moving parts of a Dash: video server, networking, and the playback client. The idea of a Dash is to dynamically streaming suitable video bitrate to the client to avoid any jitter and improve user QoE at the meantime. Current video providers such as YouTube, Hulu, Netflix are mostly based on this technology. Two major content we have seen in our network: 2D flat videos and other immersive content. Streaming immersive content still remains a great challenge from the networking side, mostly due to the content size and the limited networking resources. The current practice of streaming immersive content is using tile-based approach. The idea of using tile-based streaming and a Dash is to divide video stream to different tiles and streaming high-quality ones based on the user region of interest, or ROIs. For example, in the upper right corner, a tile-based approach divides a video frame to 9 tiles. In the bottom right figure, shows user ROI, including 4 tiles. Dash can detect this and stream high-quality videos to the client based on the user ROI. Our approach to further improve users' QoE on the network size is to optimize the ROI traffic using our AEN approach. In this figure, we show our experiment on 2D videos. So we have designed a QoE matrix in our previous paper. Here we see the QoE improvement by reducing bitrate switch count. From the left figure, our approach can lower the bitrate switch count using our AEN architecture. In the right figure, what happened here is we have 5 simultaneous video sessions. We would like to prioritize the session 1 and give a high QoS through our SDN flow control. The result here is we can guarantee session 1 can achieve the high quality videos. For immersive content streaming, tile-based approach is optimized under our AEN approach. We tested 2 scenarios. User ROI only has 1 tile included, and another one is 2 tiles included. We also simulated the user ROI movement. When ROI moves to different tiles, we also want to guarantee the user perceived QoEs. One example here is ROI. It covers 1 tile of the whole video. We established our benchmark with the traditional network, market with non-SDN. We can compare with our approach. See the right figure. We can see that we get a better average bitrate when using SDN approach. We also cover ROI movement from 1 tile to another. We call it 1 ROI switchover. ROI moves to ROI prime. In this case, our dynamic flow adjustment logic can guarantee that we still get a higher user perceived bitrate. As you can see from the result, the average bitrate we get is still higher than the non-SDN one. In overall, based on all our testing cases, our improvement for user perceived bitrate is around 100%. To summarize our contribution, we try to understand the Hadoop traffic patterns in terms of hardware usage for different configurations. We understand the impact of video streaming, and we proposed the AASD architecture, and we introduced different layers and functionalities. We showed examples of how our AA architecture works based on two examples, the ARP and the traffic engineer for rerouting. In conclusion, we developed an AAN environment with a modularized component and a fine-grained control to improve application performance. We present a SDN-based system architecture and the OTT software applications for MapReduce and Dash video streaming. Our experiment result shows promising improvement for major applications in both big data and the video streaming realm. Here are the list of our published papers. Thanks for your listening. Now I'm ready to take some questions.